In the world of statistics, another type of probability that occurs is this idea of consecutive events or repetition. When we're trying to analyze a situation, when we see repeated events occur, the same event. And so that's one case. And then we also have this idea when we sample and we're taking samples from a population, do we replace that person or thing back into the population when we sample, or do we sample without replacement? That's this other idea, whether it's with replacement or without replacement. And so when we say events, right, or we're doing experiments, we often call these outcomes trials. And when we're doing this, we're assuming the trials are independent because that influences, right? The probability doesn't change if there's independence between the first outcome and the second one. So you want to be mindful of this idea when we analyze these outcomes, that if the events are independent of each other, then we can use this idea of consecutive events calculations. We also have to be mindful, like I said, of this replacement or versus without replacement. So although we can assume that, right, consecutive trials are independent, there are cases where the probabilities between each trial does change, and thus the probabilities would be dependent. And so one such method or situation is when we're sampling from a population. In one case, it's with replacement. We replace the individual back into the population. Without replacement is when we do not replace the individual or thing back into the population, which then it reduces, right? Especially when we have small populations, it impacts the outcomes. So let's look at an example to connect to these ideas. So there's a population of 8 marbles in a jar, 5 red and 3 blue, right? This is not just imagine these are types of people, right? But we're doing a simple experiment here, a simple example. We sample 2 marbles at random, 2 marbles now. If we sample with replacement, what's the probability that the first marble is red? That's 5 out of 8, 5 red out of 8. What is the probability the second marble's red? That's 5 out of 8 because we put the marble back into the population. What if we sample without replacement? Well, the probability of a red marble is 5 out of 8. But now in the second case, we leave one of the red marbles out without replacement. It's 4 out of 7. So notice there's a change because without replacement, we impacted the outcome of the second event. So in this case, the probability of the second trial depends on the first, and the probability changes. When the sampling with replacement, the probability of our second trial is independent. So the probability of drawing a red marble stays the same because of that. All of this kind of idea and calculation is connected to what we call the 5% rule of independence. Calculations are much easier to do in the world if we assume independence between events, especially as we're sampling people from the world, right, and collecting data. So we are sampling, right, without replacement, and 2, the sample size is less than 5% of the population, and there's a little calculation you can do. Then we assume trials are independent, right? We're not replacing someone back in, but because the sample size is not that less than 5% of the population, right, then we're going to assume the trials are independent. So when you have scenarios like example 5, we can assume each trial is independent because the sample size is less than 5% of the population, right? We can assume the trials are independent. That allows us to do calculations much more quickly. In this class challenge, it may be hard. You're going to have to pause to see the calculations here. But you'll see in one case, we're doing without replacement. So doing it without replacement, you get 90 over 1,000 times 89 over 999 because you're not replacing that person. You get 8.008. Very small chance. Now, if we think about this with, just assume, right, that even though it's without replacement, assume that they're independent, we do 90 out of 1,000 times 90 out of 1,000, right, you get 0.0081. It's pretty much the identical answer. So notice, you assuming independence, because the sample size, right, 2 out of 1,000 is smaller than 5% of the population, right? We can just assume the trials are independent. Notice we don't get a different answer. So that's what this 5% rule is leaning towards, because the calculation doesn't matter. We don't need to do this out without replacement when our sample sizes are big, but also less than 5% of the population. The calculations don't change. Now, 40 subjects were randomly selected without replacement. Find the probability that they all had false positives, meaning we can look at the false positive. It's 90 out of the 1,000 again. In this case, remember, the 40 people sampled is still less than 5% of the population. So we can assume independent trials. And so what we do is we just end up multiplying, right? It'll be 40 out of 1,000 times 90 out of 1,000 times 90 out of 1,000 because of the 90 false positive. And we would do that 40 times. So it makes the calculation much easier to do. We can just raise it to the power of 40. So again, take a look at this. You'll practice it on homework, but this idea is important in statistics, especially this assuming we have independence because of the independence rule. Makes our calculations much easier to do once we meet those conditions. We end this lesson. There's no examples here. This is all terminology, right? And so we end it with this idea of mutually exclusive or disjoint events. This is different than independence. Two events are mutually exclusive if both events cannot occur at the same time. That's different than two events being independent or dependent. Mutually exclusive, they just can't happen at the same time. And you see some examples of events that are disjoint and not disjoint. Disjoint meaning mutually exclusive. Exclusive, they can't happen at the same time. Disjoint, apart from each other. Versus not disjoint, which means a student can take statistics and business at the same time. So just keep that in mind. Keep it, this idea connected to these little simple notes here also, something to make a note of. And then